Good morning. We're part of the UCI Solar Stove team. I'm Wian.
Chair.
Alvin.
Laszlo.
Ganesh.
And I'll just do a quick background on our, the origin of our stove is in a lot of developing nations. There's no infrastructure, so they use biofuels to start their fire, and they usually cook indoors because it's either cold or too hot outside, and so this causes a lot of indoor pollution. So it causes health issues. And here's a chart of who gets affected by indoor pollution. And if you do the math, it's about 8 deaths per minute. And that's one of our motivations, is to cut down this death rate. And of course, the second motivation is that we're funded by Bill and Melinda Gates Foundation. And we're doing the phase 1 program right now, where we got about 100,000 from them. So the phase 2 is due this November, and we might be able to get about $1 million on that funding. Yeah. So our goal is to develop a clean, affordable, and practical alternative for cooking. So this chart explains it pretty well. You charge it during the day, you can cook it at night. You can bring your stove in indoors, and you cook it during the night. You can store it overnight, and you can cook breakfast and lunch, and you can repeat, basically. And that's our current design of our stove. And this is a quick evolution of our stove. We started off with a double reflector, where you had a big dish and you had a small dish, and the stove sits on the bottom. The reason why we did that in the first place was so that it's easier to access your stove, and it's not bad for your back kind of thing. But we thought there's a lot of losses in that second reflection, so we moved into that single reflection. And the one on the right-hand side is the concept design for our future stove, where it's more of a heat battery, where you have your reflectors and collectors outside, and you just stick your batteries in, you charge it, and you bring it in canisters, and you just plug it into the stove. And that's the thing that Laszlo is working with. That's my goal. Yeah. And a quick run through what I've been doing. I down selected, and like I said, I experimented with this stove, and I did some cooking with it. And it took about 2 hours to charge the stove, and it got up to about 450 Fahrenheit. And we were able to cook like eggs and stuff. And well, it took about 10 minutes to cook eggs. And here's a quick result. Cooking surface temperature was about 350 C, charging time was about 2 hours, and the power output from the collector was about 20 kilowatts. And the reason why it took about 10 minutes to cook a single egg is because there's a lot of interface issues between the stove and the pan, where there's a lot of air gaps, and it wasn't in contact with the pan, so it couldn't transfer the heat, and the gradient wasn't great enough. So we kind of discussed about this. Instead of putting a pan on top, we might create a stove that it's a direct griddle, like you just cook onto the stove directly instead of having a pan. Yeah.
So I'm asked going into the current stove design, which we're utilizing, and our current stove design utilizes a truncated aluminum sphere, as you can see in this picture. This is the actual sphere right here, and then we have insulation surrounding it to reduce heat loss, and then a big pot just to be able to hold the heat as well. So moving forward. So theoretical calculations that we looked upon was, how long does it take for the salt in the vessel to melt? And theoretically, accounting for losses due to ambient temperature, due to the conduction from the aluminum sphere, and from the latent and sensible heat needed to melt the salt, we came out to, for the total time to be about 2 hours and 15 minutes if we were to use the dish that Ian just mentioned and specified at 20 kilowatts. Yeah. And basically, we have a thermal circuit model of describing the process of that stuff too. As you can see on the top, you see there's ambient temperature, and it goes through the insulation, and it goes through the aluminum sphere into the salt. And so further testing, we looked upon different types of insulation. pretty much the purpose of insulation is to minimize the amount of heat loss so that we would be able to cook over just long periods of time. And we found that fiberglass was the best match to wool, which is readily available in third world countries. The only difference between the two of them is that wool is highly flammable while fiberglass isn't. So we, most of our experiments use fiberglass. And so we found that uniformity of insulation is very important. And what I mean by that is that we have to have a uniform layer of insulation, because if it's too jagged or it's too, I guess like in a sense, too crooked, then we can't predict like the heat contained within the stove.
Okay, so my job was to move the thermal energy from the thermal salt to the cooking surface. The previous generation used a aluminum pin, as you can see in the picture on the right-hand side. The dash line in the center was the pin that was dipped into the center of the salt. That's the sphere around it. What we were considering is, can we use heat pipes as a viable option to replace the aluminum, and are there any benefits to that? We could go on to the next slide. So why choose a heat pipe over aluminum? It's simple. It's all based off the thermal conductivity. Aluminum is 230 watts per meter Kelvin. Heat pipe is 51,766 watts per meter Kelvin. That's 225 times greater than aluminum. So the design criteria was that we have to get a load, we have to move a load of 1,000 watts to the cooking surface. Cooking surface temperature has to be around 250 degrees C. The heat pipe that we decided to begin our testing with was a simple copper water heat pipe, $40 per pipe, diameter, length, and the max heat load that it can move is 140 watts. So due to the limitation of how much heat it can move, we knew that we'd have to do something with multiple heat pipes. So these were some preliminary designs that we were considering. That's the double heat pipe. That's double heat pipe where it's flattened against the surface. This is 4 heat pipes, and then bent into the center where it's coming out as a core. Go on to the next slide. But before we really began to develop more intricate designs with the heat pipe, we wanted to do some baseline testing and see if the theoretical results for the heat pipe, single heat pipe and aluminum plate match with what we're actually, the data we're getting in the lab. So I did some FEA on the single heat pipe model. That one is, the first picture over there is the temperature distribution. Once again, I applied a heat load of 140 watts to the heat pipe, and the bottom of the surface was insulated. Theoretically, the average temperature of the aluminum plate should get to 475 degrees C, which is above and beyond what we were looking for. This is just the gradient, and then this is the resulting heat flux as well. We can move on. So this is our first prototype that we designed and developed. As you can see, this is the aluminum plate. There's thermal putty in between the heat pipe and the plate itself. So essentially there's no resistance, but there's still a little bit. We bent the heat pipe in this case just because of the way we were doing it. And that's some salt at the end that's solidified on top of it. The goal of this was, once again, to see in the lab what the temperature distribution would be along the plate, and also see what the contact resistance is between the heat pipe and the plate to account for the losses. Keep going. One issue that happened was that we bent the heat pipe and we kind of ruined it. And the greatest temperature we were able to achieve with this bent heat pipe was 81 degrees C. We purchased around 10 heat pipes, so moving forward, we're going to do other more baseline tests where it's not bent, so we get the actual data. The biggest issue here is that heat pipes are expensive, and the heat pipe that we need to continuously run at the temperature, working temperature of 250 and 350 degrees of the salt, we need exotic materials, and that heat pipe, from what estimates I've gone, were around $200, $300, $400. So is it really feasible? Is it really worth it, is the question.
My part of the project is cooking analysis, and as you can see that behind any product design, you kind of have to understand what's its primary purpose for it. So cooking analysis plays a very important role in that. So I'm basically testing cooking capabilities of the existing cook stoves and comparing with that with our current salt cook stove design. And basically I've analyzed the temperatures which are required in cooking food vertically found in Indian subcontinent. It's pretty much like the Indian bread and the rice and dal which is used here. And I've also analyzed for the cook stove to cook these spots. And here you can see the temperature and the time analysis for the rice, and also the power the cook stove stated to this much power.
Okay, so what I was in charge of is basically on the topic of solar tracking. And what this basically is basically we're using the collector, and then in order to have that maximum efficiency of collecting the power from the sun, we would have to go orthogonal to the sun, so in a sense, sort of tracking the sun's location. And so what I did in this tracking is basically I needed to analyze the trade-offs and to see whether or not tracking is a necessity for this design, whether or not tracking compared to no tracking, will it be, is the efficiency difference that much different for us to incorporate in our design? And so in order to, before we start going to the design of solar tracking, we first must track the sun and sort of understand the background on how the Earth and the sun rotate to one another. So there are a lot of factors that needs to be considered before we start tracking the sun, and this includes basically the days of the year. The days of the year is very important in the sense that each day of the year, the location of the sun is changing relative to Earth. So so these two terms, equinox and the solstice, is basically two terms. Solstice is where the sun is at the peak or lowest of its height, and then equinox is at the middle. So those two sun locations need to be considered, and then there are also angles of the sun relative to your position on the Earth. And this includes, I won't go into detail of each one, but it includes angles of declination angle, azimuth, incidence, and elevation angle. And so overall, I did some calculations on the efficiencies of basically tracking and no tracking. And so since the sun rotates, or the Earth changes its position relative to the sun, the efficiencies change throughout the year, throughout seasonally. And so these are all calculated efficiencies for our design, and relative, they're all approximations. They're not exactly accurate, but it's a good general overview for our design experiment or project. And so this is pretty much a graph of comparing tracking during continuous tracking over years, and also in terms of no tracking, the power on how the collector collects all the power. So overall, we aim to basically manually adjust our solar stove mechanism, where we have to adjust to track the sun. Yeah, that's pretty much the gist I can give you for the solar tracking. There's a lot more detail that I can go into.
Just to end off the presentation, we just want to give you a slide about the funding that we have, because we kind of weren't clear last quarter about funding, but like I said, we got about 100,000 from the foundation, and 80,000 funds Michael back there, and he's the lead graduate student that does the research on the stove, and 20,000 goes to equipment and material. We're currently in the middle area right now, where we're trying to raise more funds so we can do a little bit more research during the summer to get prepared for the phase 2 proposal, which is worth about $1 million, and there's other stuff that we're seeking too. So that's our quick breakdown of our funding. And this is our development plan, and we pretty much covered everything in that first phase, where, like I said, we're in the middle columns. We're in the second phase, and we're writing out the proposal, we're prepping for a proposal, and yeah, we're going to start moving forward from here. Thank you.